Hi everyone, this is the first in a two-part lecture about magma and igneous rocks. Last week we had been discussing minerals and the elements that make up minerals and how they're bonded together. So just as elements make up minerals, minerals make up the rocks of planet Earth. So since this lecture series will ultimately culminate in the discussion of igneous rocks, we are now moving on to the very important rocks part of the semester. I thought we'd start by defining what exactly rocks are. Okay, so if you had to kind of fill in the blank here on giving a definition of rocks, I think you all know what they are intuitively, but let's define it together as a group. Rocks are considered coherent, meaning that you would need to use a hammer or something to break them apart. If you had just disaggregated mineral grains, that would not constitute a rock. So rocks have to be coherent solids that are naturally occurring, just like minerals. And we consider them to be aggregates or collections of different minerals. Sometimes rocks are made of only one mineral type, and more commonly they are made of many different kinds of minerals. So to restate, rocks are naturally occurring coherent solids that are aggregates of minerals. All rocks belong to one of three principal families. They can be igneous, metamorphic, or sedimentary. And these types of rocks are all related through processes governing the rock cycle, which we'll talk about later. We're going to begin our discussion of rocks by talking first about igneous rocks. But I want to just go back to this concept of rocks being coherent solids. So how are they coherent? What holds them together? And in their most fundamental way, we could break down all rocks into those that we consider to have clastic texture. So in rocks that have clastic texture, the minerals that make them up, so the aggregate of minerals that comprise these rocks, are held together with some kind of a cement. You can think about this as like a glue that precipitates from water that binds the minerals together and holds them into an aggregate solid. In contrast, you can have minerals that we consider to be crystalline. The rocks that are made of minerals that are held together in a crystalline texture are coherent because those crystals interlock with one another to form like pieces of a jigsaw puzzle. And it's that interlocking nature that holds the rock together. So igneous rocks, for the most part, have this crystalline texture to them. Igneous rocks are formed through the crystallization of cooling magmas. So let's start there. What is a magma? A magma is simply molten rock or melt. Sometimes we just use the expression melt, that exists within the interior of the earth, so below the surface of the the surface of the earth. So an igneous rock can be one that forms from the cooling and crystallization of a magma within the earth. It can also be one that forms from the cooling and crystallization of a lava on the exterior of the earth. So lava is simply melt that exists outside of the earth or at the surface of the earth. Okay, so magma and lava are equivalent terms, only we use magma to describe molten rock or melt below the surface of the earth, and lava to describe melt at or above the surface of the earth. An igneous rock that cools and crystallizes from a lava at or above the surface of the earth is considered an igneous rock that is extrusive because it forms on the exterior of the earth. An intrusive rock that solidifies within the interior of the earth is considered intrusive. So interior, intrusive, exterior, extrusive. Extrusive forms from lava, intrusive from magma. The extrusive realm. Sometimes magmas make it all the way to the surface, and when that happens, they can be vented dramatically through volcanoes, producing really exceptional volcanic eruptions. So those eruptions can take a number of different forms and can produce different extrusive rock products. We'll look at some of those. A volcano is, by definition, a vent that connects magma from the interior to the Earth's surface. We also use the term volcano to describe the edifice, so the mountain that is constructed via multiple eruptions of volcanic material or extrusive igneous rock. So when that magma makes it to the surface, it gets extruded as lava, and that lava can then flow due to gravity down the slopes of the volcanic edifice. That's what's shown on the left. Sometimes coming into contact with vegetation and burning it, like you're seeing on the right. A picture on the left here shows one of these lava flows that ultimately is coming to a stop because once the lava meets the surface of the earth, it all of a sudden does not have the insulation of the surrounding warm rocks in the earth to keep it molten, so it will start to cool, and at the exterior of the earth it cools fairly rapidly. And when that happens, the chemicals that were bouncing around in the liquid state of the magma start to lock together to form minerals, and eventually those minerals aggregate and join together in a jigsaw puzzle to make a crystalline igneous rock. So the lava that was once flowing down the mountain or down the volcano cools and crystallizes to make the igneous rock that you see in this picture. And you can imagine with a repeated eruption of rock like that, you could produce the cliff faces that is shown on the bottom right-hand image here. So these are ancient lava flows exposed in the walls of a canyon in Hawaii. The way that magma and lava cools and crystallizes to form igneous rocks varies quite a bit depending on the composition of the magma or the lava and where on Earth it is cooling and crystallizing. So in the upper picture, you can see that the picture in the upper right corresponds to this little box here. So we're looking at an igneous rock that formed from the cooling and crystallization of lava at the surface of the earth. And that lava flowed down the volcano and cooled and crystallized to make these flows that you see here. So here's one flow. And beneath it is a pyroclastic layer. So pyroclastic layers form from the superheated eruption of gas and ash that goes rocketing like an avalanche down the volcano. So that's what's shown on this side here. And when this cools and crystallizes and quenches into an igneous rock, it forms a pyroclastic layer. Whereas a lava flow, like this one here, might form something that looks like this. And you can imagine that a single eruption from a volcano like this might produce both. And so you can produce these stacked layers of lava flows and pyroclastic flows. And that's what's intended to be shown here by the stripy look of the volcano. Of course, magma can also crystallize deep within the earth to form an igneous rock. And so what you're seeing in the picture on the right might represent this little box here, where you have igneous rock, that's this pink stuff from cooling of the magma chamber, that is being injected by another magma chamber that is kind of shooting its way up into here, and that would be this black dike here. And we'll discuss what a dike is later. So when we meet together to talk on our live Zoom chat, I'll ask you this question then, but you might want to pause your video and think about this quiz question that asks you, what is the difference between magma and lava? We'll return to this when we meet together. Okay, igneous rocks form from cooling magma, but how is magma made in the first place? I've told you when we discussed plate tectonics and the layers of the earth that the only part of our earth that is liquid is the outer core. The mantle, the crust, and the inner core are all solid rock. That means that in order to produce magma or molten rock, very special things have to happen, phenomenal things. The Earth is not a big sea of molten lava. It is solid rock. And it's only under very special circumstances that you can get small parts of solid rock in few places in our planet to turn into melt. And so what I'm going to do now is walk you through the three main ways that we can produce magma within the Earth. The first is through a process called decompression melting. And so to explain decompression melting, we're going to look at a figure from your textbook. And what this figure intends to show is the relationship between temperature in the Earth, that's on the X or horizontal axis. As you go to the right, temperature is increasing. And temperature is changing as a function of both pressure, as we go down on the left here, and depth. And not surprisingly, depth and pressure in the Earth are linked to one another. So the deeper you are in the Earth, the greater the pressure. The solid black line in this diagram is the geotherm. And the geotherm is a term that describes temperature changes in the Earth. I'm going to abbreviate that as a capital T. Temperature changes as a function of pressure or depth. We could think of it either way, as a function of depth. Okay, so as you go down in the Earth, you can see the temperature is rising. That's what the black line shows. But everywhere in the Earth, even though temperature is increasing, and the Earth is a very, very warm place, the warmth of the Earth is left over from its original beginnings as it cooled from a molten kind of ball of lava or magma. It also has radioactive elements that produce heat. So the Earth is a very hot place, a very warm place. But the interior of the Earth, despite its high temperature, is a solid, mainly because pressures are also very high. So the pressures force molecules to bind together as minerals and rocks. They're not allowed, they don't have the space to move around and be liquids or gases. There are certain circumstances, however, where you might allow the Earth, that is otherwise a solid, to partially melt. So the green line that's shown on this diagram here is the solidus. And the solidus is the line at which the solid Earth begins to melt. The red line here, the liquidus, is a line in pressure, temperature, space that describes where the Earth, or a very small portion of it, would totally or completely melt. It's very rare to have any part of the Earth intersect with or cross over the liquidus. But we could somehow get a piece of the Earth to cross over that solidus and start to barely melt. And one way to do that is simply through decompression. So if you take a rock, a piece of the mantle at point A, and you decompress it, that means you're going to bring it up in this diagram, because remember, pressure is one of the vertical axes, and pressure is increasing towards the bottom of the chart. But if we take rock A and we somehow physically move it up like so, you can see that it could, without even changing temperature, intersect that solidus and start to partially melt. And there's a couple ways you can do that. You can either move the mantle upward, or you could remove some of the mantle that's on top and therefore decompress the rock. And so this happens on the Earth in a few different settings. It happens at mantle plumes. Okay, so in each one of these pictures, the dashed black box represents a part of the mantle, the asthenospheric mantle, that is decompressing. And over time, that decompression causes melt. And the melting that's being produced are these little red dots and stringy blobs. So in a mantle plume, you guys know this because we talked about Hawaii quite a bit, molten rock from deep, deep, deep within the earth starts to rise up. Well, as you rise up, you're decreasing in depth and you're decreasing in pressure. You're going up after all. And so that depressuring causes that mantle to eventually intersect with the solidus and partially melt. So that can happen via a mantle plume, or in this case, beneath a rift or a mid-ocean ridge. So down here we've got the case of mid-ocean ridges. We've talked about those a lot. At a mid-ocean ridge, you are ripping apart the lithosphere, and when you do that, you're essentially removing the overlying mantle on top of this little box here, and so you're causing it to decompress. And when that mantle rises up, it starts to melt, producing the magma that then flows out to make the lava that cools to create the basalt of the ocean floor. Okay, so we've discussed decompression melting, but what about other types of melting? Well, the second most common way to make little pinpricks of magma within the earth is through something called flux melting. Flux melting occurs when water or other volatiles are introduced to solid rock. That lowers the melting temperature. And when that happens, magma can form. So let's look at this diagram of a convergent plate tectonic boundary, where two tectonic plates are converging or crashing into one another. When that happens, if one of the plates is an oceanic plate, it will subduct. Okay, so here we've got a subducting oceanic slab on the left, and then we've got an overriding continental plate on the right. Well, as this subducting slab moves down, down, down into the interior of the earth, it starts to get rid of some of the volatiles that were bound in minerals of the oceanic crust. And those volatiles get released at depth. So that's what these arrows are showing here. And those volatiles, by the way, could include water. They could include CO2. Those are the most common ones, but there are some others. And when those get released into the asthenospheric mantle right here, it causes the mantle to partially melt because the melting temperature is lowered. Okay, so remember I told you that rocks deep within the earth, even though they're hot, will remain solid because they're being held together by pressure. But you can change that equation simply by adding water or other volatiles, because that at high temperatures will produce melts by lowering the temperature at which melting can form. Once you've made those melts, of course, they are buoyant and they will rise up through the mantle. Some of it might pond here near the moho. Some of it might make its way into the crust and crystallize beneath the surface of the earth. And some of it might make it all the way up into volcanoes and spill out. So again, flux melting occurs when volatiles are introduced into the hot mantle, thereby lowering the melting temperature of that mantle. By the way, this is how continental volcanic and island volcanic arcs are formed in subduction zone settings. Okay, so now we've just hit on both of these. And lastly, there is something called heat transfer melting. This is probably like the easiest thing to imagine. And in heat transfer melting, rising magma can cause the temperature of nearby crust to increase and to melt. Your textbook gives the example of putting hot fudge on ice cream, and where the hot fudge touches the ice cream, it will start to melt, simply because you've significantly raised the temperature of the ice cream at that contact between the hot fudge and the ice cream. Okay, so in this picture, we've got melt that is rising up through the lithospheric mantle, and in this case, it's ponding right here at the moho, the boundary between the mantle and the crust. And so imagine that you're parking a whole bunch of liquid magma deep within the earth here at the base of the crust. Well, that's going to make the crust that's right here really, really hot, right? And so just by increasing significantly the heat to this lower crust, you can cause kind of small volumes of new melt to form. And when that happens, we call this heat transfer melting. You're transferring heat from the primary melt, this orangey red stuff, to the lower crust and producing a new magma, which is the yellowish orange melt. Okay, what is magma made of? Right, so we've discussed all of the different ways that you can produce magma in the earth. We know that magma is produced in the interior of the earth. Some of it makes it to the exterior to form lava. But what the heck is magma anyway? Well, it shouldn't surprise you to learn that most magma is made of Si and O. Because of course magma cools to form rocks, and you already know that most of the rocks of our earth are made of silicate minerals. So it makes sense that the magma would be mostly silicon and oxygen, and it is, plus variable amounts of other elements like calcium, potassium, magnesium, iron, sodium, aluminum. These are the big players in terms of elements in the earth. Magma can also have variable amounts of volatiles, and if it has a lot of these volatiles, we would consider it wet, and if it has very few volatiles, we could consider it a dry magma. So magmas can have a whole range of compositions, and in the next lecture, so part 2 of Magma and Igneous Rocks, we're going to talk about what exactly controls this whole range of compositions and what kinds of igneous rocks result from these different kinds of magmas. Because magmas can have Si and O as, like, you can think of that as being like the batter that makes up most magmas. Okay, it's mostly silicon and oxygen. Therefore, we can classify kind of to first pass categories of magma based on how much Si plus O they have. So a magma that has 66 to 76% of its weight SiO2, if those silica tetrahedra make up anywhere between 66 and say 3/4 of the magma by weight, then that's a very high silica magma, and we call it felsic. That's the name we give to a magma type that has a lot of SiO2. At the other end of the spectrum, you could have a magma that is very poor in SiO2. It still has a lot because remember, those are the most abundant elements, but it could have as little as, say, 38 to 45% of its weight being SiO2, or it could have maybe a slightly higher amount, approximately 50% of its weight being SiO2, and in that case we would call the magma mafic, okay, or maybe even ultramafic if it has very little. Mafic, by the way, is a word that comes from M for magnesium, so the Ma for magnesium, and the F for iron. So something that is mafic does not have very much SiO2 and instead has magnesium and iron, okay? Something that is intermediate is just like what it sounds, so halfway between something that is mafic and that is felsic. And this is very important. We're going to continue to talk a lot about the SiO2 content of magmas because it controls the temperature of the magma, the viscosity of the magma, and its density. And of course, those things are really important when we think about what kinds of igneous rocks form from these different types of magmas. Make sure to watch part 2 of Magma and Igneous Rocks.